Thank you. Okay, so I have the benefit of having seen not only the titles but the whole slide set for the previous speakers before I even wrote my own title or started even thinking about my slides. So the talk theme is going to be trying to leverage the tools theme that they introduced before me. And I'm going to focus on new tools, newer tools, even sort of next generation tools. I'll be building toward that throughout the talk. I'm going to start with a few general words about tools. First, just to remind you that John's talk, two before me, made quite explicit use of the idea of a toolkit. And although he didn't develop it so explicitly as Rob Hinchy did, his whole talk was about tools and toolkits. And even his title even had the questions: do we have the tools we need, and do we know how to use them? The report, the workshop that a bunch of us were at in last summer in Seattle, there was a precursor to this session here, produced a report. And if I did a little word map of this report, you can see what's on the screen there, which shows you just how prominently the concept of tools was in that report. And then the statement of need that many of us are thinking about submitting proposals to coming in a few weeks also really revolves around this idea of tools. And so tools are going to be the theme. And so I want to develop some more generalities about these tools. And the first point here will be about the function of the toolkit for us. And the obvious primary reason the thing exists is so that we can manage or remediate more sites, better, faster, cheaper, right? That's been the obvious motivation. But there's another aspect to this that hasn't been mentioned so far today, I think often gets overlooked, and I want to make the case that it's very nearly as important. And that is that the tools are the currency on which you all compete with one another. So both as individual practitioners, as companies, even as agencies, you basically compete based on your toolkits. And you invest a huge amount of time and energy into developing, refining, and improving your toolkits, because that's the basis of the competition. And that's what makes this community, this industry, this ecosystem function efficiently is that competition among the toolkits. So what makes a good toolkit? There's a number of, again, relatively obvious characteristics. So it's not so much that the toolkit needs to be big. Often one might presume that, but big per se isn't the critical characteristic. Complete, perhaps, is a better choice of words there, and or balanced. The toolkit also needs to be ready, and ready in the sense that I mean organized and understood such that you can deploy it on the challenge at hand. And so this is riffing a little bit off of Rob's point in the previous talk about how sometimes we have tools, but we don't really know how to use them as well as we might. The toolkit presumably populated with good tools, so tools that are proven, and the tools need to be the new tools. And so this point here is a little bit different than the previous speakers, and I use these two graphics that I got off the web to try to illustrate the distinction. So clearly the picture on the top is a toolkit that's full of a lot of good tools, and they are maybe sufficient to do the job. But the guy that has the toolkit that's pictured below has got a toolkit that's better organized, and most importantly, it's populated with the newest and the latest state-of-the-art tools. And even though both toolkits may be sufficient to achieve certain goals, the guy that has the toolkit on the bottom is going to win in the competition. And so there's a built-in incentive for improving, developing, advancing the toolkit that comes from this competition element, which is, like I said, is often neglected in your thinking about this. In addition to that, the toolkit necessarily has to change because other things change. And so this innovation diagram here, I adapted to illustrate the dynamics of this. So on the bottom axis there, you have the tools that are changing from established tools to new tools to emerging tools. And on the y-axis, you have the challenges that drive those innovations evolving. And those changes can take place both in terms of contaminants, so emerging contaminants. You also have emerging priorities. And so there are changes in various kinds of externalities that drive alterations in how we prioritize what we're trying to do. And both those things drive changes in tools. So as long as those things exist, change is inevitable, and therefore the toolkit has to change, and then if you're going to be competitive, you have to have a toolkit that keeps up with these changes. One more point about this is that the tools are not just applicable in their particular context that they originally arose. So for example, if you look at the lower left corner there, the green sphere, maybe that's where we presume this particular session, chlorinated solvents, belong. So it's established challenges, established tools. But when we apply an innovative technology to that established challenge, we move across the vertical interface to that yellow quadrant in the upper left. When we apply our tools that we develop for chlorinated solvents to new emerging contaminants, we move across the interface from left to right. And generally, one doesn't leap from the lower left corner to the upper right corner to solve the PFAS problem. You go either left and then up, or you go right or up and then right. And so the tools are transferable, and so tools are a good investment regardless of how they actually end up getting used. And then one last point, the last one on the bottom, the toolkit is transferable between colleagues. And it's essential that we do that. And so I guess it was Rob made this point a little bit indirectly. This community is an aging community. And so as those people that have developed their toolkit move on, retire, they should be passing that toolkit on to their junior colleagues. And many of you that are in the practitioner industry realize that you spend a great deal of time cultivating your junior colleagues and passing that toolkit on. So it's a really essential part of what we need to be doing. And so in order to play that up a little bit, notice the little hand that came up in the upper right corner of the screen there. So during the next couple of slides, or bunch of slides that I'm going to go through a variety of tools, I'm going to poll you and ask you, how many of you remember before you had that tool in your toolkit? And we'll see how this goes. I think it'll be interesting. All right, we'll start with a very established tool, and the one that's near and dear to my heart, the one that I started with, zero valent iron and permeable reactive barriers. So just a tiny bit of history for those of you, the younger ones of you in the audience that might not know all that. The watershed event that really triggered the origin of the whole ZVI thing was work done by Stephanie Johannesson and Bob Gillam's lab back in the early 1990s. That led to a publication in 1994, which really is the discovery of the utility of zero valent iron for degrading contaminants. Right about the same time, there was work going on also at Waterloo, I think kind of between David Bellows and John Cherry. I don't know the details of how they were interacting on this, but it was also reported around early 1990s or so, and that was the idea of permeable reactive barriers. So they needed to fill the permeable reactive barriers with some sort of medium, right? And so Gillam and Johannesson had the medium that was the ideal one for that purpose. And so from that, you get this intersection between the two spheres in the Venn diagram on the right, where the concept of an iron wall came about. A little other historical things of interest here. The animated GIF in the lower left comes from the original ETI, Environmental Technologies website. That's long gone now. It probably was the first animated GIF that any of you in this room ever saw. And the thing on the right, this Venn diagram, I drew in the maybe late 90s for work that we were doing, never published. It's actually still available online at that URL that's on the bottom of the page there. That's a web page that I did a long time ago. Haven't updated since 2005. So you would take it with a grain of salt if you decide to go look at that website. It's sort of a historical snapshot of what we thought about ZVI back then. All right, so how many of you remember before a ZVI PRB was part of your toolkit? Just about what I expected. That's maybe 10% of the room, something like that. So 10% of the room is that old. Okay. So next, in situ chemical oxidation. So I lump the three major versions of it here: Fenton, activated peroxide, permanganate, and activated persulfate. The genesis or the history of this, I tried to put together a little bit accurately for the purposes of this slide. The applications of peroxide in the sort of Fenton formula to groundwater seem to arise somewhat, again, late 1990s with Watts and Segrist permanganate, also 90s with Segrist and Farquhar, and then Schwartz and Hoag. Persulfate, more Hoag than anybody in the early 2000s. and then lots of others have picked up on these things. It's hard to track down the original use of the term in situ chemical oxidation, but Bob Segrist said to me that he was using that terminology routinely in the 1990s. And so now we have all these documents and books, and it's clearly now a well-established technology. So I have it, the heading there says an established technology. And so now again the question is, how many of you remember before ISCO was in your toolkit? Almost the same number, which is about what it should be based on my timeline. All right, so let's move forward. So to provide a little roadmap for that, I've used this timeline thing that we all take out of Hans Strue's talk, which is primarily a map of CERTIP initiatives that are relevant to chlorinated solvents and tools applied thereof. There are two. He classified them in this color scheme here. So he's got red is technologies, and then these other three here, green is complexities, purple is characterization, and blue is decision support. I'm going to use the technologies distinction here. I can't really make much use of the distinction between those three here, so I'm going to lump those together, and I'm going to call that basically conceptual tools. So I'm going to have sort of a gradient here between conceptual tools and technological tools, and then a few tools that are kind of a little bit in between. And so in addition to the chronological continuum that we're going to proceed from older to newer, we're also going to kind of jump back and forth a little bit between conceptual and technological tools. All right, so now I'm calling these new tools, and in this case, they're both kind of hybrid technological conceptual. We can debate that issue later to anybody that wants to talk about that. I put two of them on one slide because I don't know very much about either of them. One on the left is MBTs, and the other one on the right is CSIA, so molecular biological tools and compound-specific stable isotope analysis. With a little help from Frank Loeffler, I determined that MBTs, the first real application of semi-quantitative PCR to groundwater was 2002, Dave Major paper in the ES&T. And about 2003, they were already doing qPCR in groundwater, and obviously there's been a whole lot of development since then that was alluded to, I think, in John's talk, or elaborated a little bit in John's talk earlier. With respect to compound-specific isotope analysis, I searched my EndNote database for early papers on that, and interestingly, the oldest one popped up was from Ramon Aravena, who's at, I think, Waterloo. But then a bunch of papers by Barbara Sherwood-Waller, and then Rene Schwarzenbach and his proteges, Martin Elsner, and Thomas Hofstetter. Now notice the dates on the slide here. We're talking now early 2000s pretty much for both of these new tools. So again, how many of you remember before MBTs were part of your toolkit? Good, this is working. So we're getting a good third of the room now. And maybe CSIA, is that different? Ooh. Slightly fewer people. That's interesting. Okay, so we're about a third of the room. So we're going to keep moving forward here. So new tools, and I think this is going to be a newer tool. And now this one is purely in the conceptual category, and it doesn't have a really great name. I'm calling it Diagnostic Pathway Product Branching. And so this is basically the idea that hydrogenolysis of chlorinated solvents produces products that tend to accumulate these infamous Stahl intermediates, and that is characteristic of biotic dechlorination pathways. And in this scheme on the right here, which is adapted from the scheme that was originally drawn by Bill Arnold for his work, the solid arrows on the right side of that scheme are the hydrogenolysis steps, and as you see, it goes from PCE to TCE to DCE to vinyl chloride, and then the ones that are circled in the colored sphere are the Stahl intermediates. So in the abiotic system, there's a tendency for it to go another way, which is reductive elimination, and that's the left side of that scheme there, and that has the very convenient or desirable characteristic that it bypasses those Stahl intermediates, and it can get you to complete dechlorination without any of the accumulation of those unwanted products. Now, this has turned out to be quite an influential concept in this field. And so I'm calling it a tool. I think it's an important tool. It's a conceptual tool, and it's moderately new. So now the question is, how many of you remember before you knew this, before you had this tool, conceptual tool in your toolkit? About half. Okay, so So my point is that these tools, many of you didn't have these tools all that long ago, right? All right, so we're going forward a little bit more. Abiotic natural attenuation. On this slide, I lumped together in situ chemical reduction on the top and abiotic natural attenuation at the bottom. Sometimes the distinction between them is a little bit blurry. The in situ chemical reduction really arose as a way to bind together a bunch of ZVI derivative kinds of water treatment processes. But then as we started to think about what it should be, we basically started lumping in more and more types of abiotic reduction processes. Abiotic natural attenuation grew more out of the natural attenuation world. It is really focused on reduction of chlorinated solvents by mineral phases. I would point out that, like many of these things, nothing is really completely new. So in the case of, say, abiotic reduction of contaminants by mineral phases, on the second bullet in the second section there, I reference a paper by Macaletti in 1986. I was co-authoring that paper when I was a graduate student. The title is Abiotic Reduction of Contaminants by blah, 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 blah. It's in Journal of Contaminant Hydrology. It's Volume 1, Issue 1, Page 1. All of that was that long ago, but the idea that has largely been popularized by, essentially consecrated by John Wilson, the idea that there's abiotic natural attenuation is a significant aspect of natural attenuation only kicked in really quite recently. And that basically is justified by the scheme on the right, which is a beautiful figure that was become available just recently and has been reproduced in a bunch of different places that illustrates all these different types of interfacial dechlorination reactions that occur on minerals that form in situ, ultimately driven by microbiology, but the point of these figures is that the contaminant degradation step occurs on the mineral interface, and the microbe is actually one step back upstream, removed in that. And I would point out the details to you, but the configuration of this room and laser pointing like this is not going to make that possible. Okay, so one point I want to make before I leave this is that there's a new twist in this down here at the very bottom. The last bullet I added as an afterthought. There's a brand new paper by Charles Schaefer, and this is, again, not completely new science, but I think it's going to be new in the sense of getting traction with this community. And that is the idea that there's probably oxidative contaminant degradation pathways that contribute to natural attenuation, also in this sort of abiotic way. And exactly where that will go and what it will amount to in the long run remains to be seen. I guess the point of using this cover slide here was to try to justify the generalization that this is also now abiotic natural attenuation has become a pretty widespread, widely accepted concept, but it's pretty new. So again, how many of you remember before you knew any of this, before you would have ever invoked ANA? About half. About half. Okay. All right, so now newer, I think, even newer, sulfidation. So again, nothing is really completely new. There was work on the role of sulfur impurities in the reactivity of ZVI ages ago. There's also work on reactivity of iron minerals with chlorinated solvents. Also goes way back, Kim Hayes, Martin Reinhardt, et cetera. But very recently, the idea that modifying iron phases, particularly ZVI, with sulfur had very profoundly significant benefits is just really kind of caught on. And so that really was driven by this work, originally by this work that was my PhD student, Demin Fan, and is illustrated by this TOC art figure quite nicely, where on the left he has shown what happens if you just use nano-ZVI on chlorinated solvents and water, and basically measure the electron efficiency of the reduction. So basically how much of the reducing equivalence from the ZVI goes to reducing water versus the chlorinated solvent. And on the left you can see the blue bar, it almost all goes to the water, and very little goes to the chlorinated solvent. That's very inefficient. When you sulfidate the NZVI, it's inverted. So most of the electrons go to the TCE, and very few of the electrons end up going to water. That's a dramatic change and fundamentally alters the potential usability of nano-ZVI. It's completely replaced any interest really in bimetallic ZVI. There's quite a few vendors of iron materials for remediation that jumped on this bandwagon just recently. So there's quite a few products now that are available. And there's even, I think, a few vendors of iron sulfide materials are also leveraging this to their benefit. Now, this, I'm not so sure how many of you would consider this to be part of your toolkit yet. So I'm going to invert the question, and I'm going to say, how many of you remember, how many of you consider sulfidation to be part of your toolkit? So in this case, buying sulfidated products for treatment of sites. Just a few, just like maybe a dozen at most. So that's clearly quite new to this crowd so far. Which means that the rest of you haven't caught up with that train yet. All right, so now one more. Black carbon amendments. John Wilson alluded to this in his talk. So by this I mean all varieties of black carbon. So that would include granular activated carbon, GAC, but also other sort of pyrogenic carbonaceous material, including things like biochars. And so once again, there's the old and the new. So there's the traditional applications of activated carbon to absorbing contaminants in ex situ filters or supporting biofilms, and that goes back way far. On the timeline in the right of this figure, which comes from a review paper that Demin Fan again did, the blue bar at the top and the green bar at the top and bottom of that figure are those older applications of this technology. But then fairly recently, it's become pretty well established that you can combine carbon with other things and have it be useful in situ applications. And probably the clearest example of that is this product BOSS 100, et cetera. And that's been commercially available for a while, and it appears to be pretty successful. And so now, even more recently, there are these sort of colloidal activated carbon blends that are being combined with various things for various advantages. And the Regenesis product, Plume Stop, I think is probably a good example of that. So now the question would be, how many of you remember before, well, maybe we'll, again, use the new version of the question. How many of you consider these carbon amendments to be part of your toolkit? Okay, about a third of the room are good. So you're more up to date on that one. So that's good. And then I would point out here is that this train hasn't stopped moving yet. And so I just wanted to give a little call out here for the bottom bullet on the bottom left there for a new project just funded by CERTA that I'm a co-PI on, that's led by Wen-Queen Su, who's at Villanova. And in that particular project, she's chemically modifying activated carbon to impart specific functionality that should allow it to do some water treatment things that it can't otherwise do. So in particular, shown on the top there is it's able to bind to a contaminant like NTO, which otherwise really wouldn't stick to activated carbon. And in the bottom, she's showing that if she modifies it appropriately, she can hydrolyze energetic materials on activated carbon. Again, activated carbon isn't normally considered to be a catalyst for hydrolysis. Almost done. So last example here. So I'm calling this one a future tool. Because I'm pretty sure that almost nobody in this room has heard of this up till now. This is, we're going to name it Reactive Mineral Intermediates. I'm going to call it, given the acronym RMI. The hypothesis, right now it's still kind of a hypothesis, but I predict that it will be a technology before long, a conceptual technology. And so it goes like this. Active precipitation leads to metastable mineral phases that serve as reactive mineral intermediates, RMIs, which are the primary thing that produces abiotic natural attenuation. And so let me illustrate that with this cover art from a brand new paper by Michelle Shearer. This is the work that got the Project of the Year award a few minutes ago down in the big ballroom. And so in that work, Michelle was studying TCE degradation by magnetite. And the original goal of the project was to try to figure out how fast that reaction would really be. But as you can see from the big bottle on the left, she really couldn't get any real reaction out of that system alone. When she added a little iron 2 to it, which supposedly is supposed to kind of charge up the magnetite, she still didn't really get any significant amount of reactivity. Unless she modified the conditions to the point that it started to generate FeOH2. And once she started to precipitate that phase in the system, the degradation of TCE started to kick in. And so her experimental data in support of this looks like this. These are speciation diagrams where she's got iron concentration on the Y, pH on the X. And so in the gray region in the upper right corner is when FeOH2 precipitates. In the unshaded region in the lower left, it has not precipitated. The open dots that are that open gray circles are where she didn't see TCE reduction, and the solid red circles are where she saw TCE reduction, and clearly TCE reduction goes together with formation of FeOH2. So the implication is there that this phase is essential. So a newer version of this is a paper of mine that just came out a few weeks ago. It doesn't have page numbers yet. And in that study, we were studying the kinetics of production of hydrogen from ZVI. And we have lots and lots of data, and we did an elaborate kinetic model on this. And if you can see from the shapes of those modeled curves in those figures, they all have a kind of a bimodal, steep, and then a plateauing shape to them. And the steep part at the beginning turns out to be explicable using the very same concepts that were implied by that work of Michel's that I just showed you. So the idea is that there's a metastable intermediate phase that forms initially due to the conditions of the experiment, and it gets used up. In this case, it gets used up, so there's none left. And so that part dissipates, and then the slower reaction takes over. So before I go to the next slide, let me go over the sort of general characteristics or implications of this RMI concept. First of all, it's formed in situ. So we didn't mix it up outside and put it in the bottle. So you put it together, you put the system together, and the phase is formed in situ. It's highly reactive, and so it's easily lost. So it reacts with all kinds of different things. And so together, those things means it's metastable. So there's a flux in and a flux out. And as long as the two things are in balance, then you end up with a metastable phase that may be in steady state. But if they get out of balance, it becomes a transient phase, and you lose it. And so any of you that know photo degradation of contaminants will be very familiar with this in terms of reactive oxygen species. So that means that you can't really isolate it. It makes it very difficult to study from the point of view of, say, taking core samples and bringing them back to the lab. But it can be important in degrading contaminants. So one last part of this is to show that we have data that supports this also from column studies. So this is from Rick Johnson's project, ongoing, that I'm co-PI on. And he's running a whole bunch of columns in the lab where he's got the series of them are shown there. They're magnetite sand mixed columns that are either just water with lactate, with nitrate, with sulfate, etc. And those columns have been running for a long time, so they're presumably in a kind of a steady state type of condition. And so they see TCE, and he gets degradation of TCE. But there's a really interesting feature here. So if you look at the bottom blue points in the bottom of this graph, that's the kind of rate on the y-axis. That's the rate of TCE degradation by the column materials that he packed into the column without any aging. And the rate is 0. At the top of the figure, there's a green line, which is the rate of TCE reduction by the column in its continually flowing age state. It's quite fast. So on the right side, you'll see there's calculated half-life projected for in situ conditions of about 1 day. But when you turn the column off, it decays. So you see the red line, it drops off quickly from being fast to being hundreds of days. And that part is evidence for this reactive mineral intermediate idea. So it's as long as it's steady state, the TCE degradation continues to be like the green bar. But as soon as the conditions are, what makes the conditions are changed, you lose the reactive mineral intermediate, and the degradation rate drops off. And so you realize this has very broad implications for interpreting sites that have abiotic natural attenuation, because this reactive mineral intermediate phase is a very hard thing to pin down. You can't easily see it, and you can't easily measure it, and it's dynamic. It's going to arise in some situations and not in others, and it can be a problem. So to summarize, this toolkit is the currency of this field. It primarily exists to clean up sites nominally, but it's also the basis on the competition between all of you, which is what keeps this community healthy and effective. And this toolkit includes technologies and it includes concepts, and those two things are compatible. The toolkit changes, and it has to change. Obviously, because the challenges change. Emerging contaminants come up, that changes the toolkit. Priorities, SERDP writes a different RFP that has a different focus, and that changes the priorities, and the toolkit evolves with it. It also has to change because of this competition element. So in order to be competitive, you need to have a better toolkit than the other guy. And that necessitates change, even if we already had good enough tools to clean up the site in the first place. That's not good enough, because if you're going to stay in this business, you need to have a better toolkit. And the last point there, that leads to this propagation from new tools to emerging tools to future tools. And then I'll just skip to the very last bullet. I want to reiterate this idea that this is a community of people, and there's a bunch of people here that are older and are retiring or soon to retire, and there's a bunch of younger people in the room that are just learning this stuff, and they need to acquire the toolkit that the prior generations have developed. And passing that on is a big part of this process. And certain projects that are funded to universities that train graduate students are the people that you're hiring that have the tools to keep that pipeline primed. Thank you.